You guys have graphed quadratics before? Let's start with y equals x squared minus 4. What's the y-intercept? What's the x-intercept? How do you know it was plus or minus 2?
Well, assuming y is equal to 0, you add 4 to both sides. And you get x squared is equal to 4. Square root of that.
Okay, so that's for that graph, for that line. Okay, so let's do the same process for y equals x squared plus 4. So this time y-intercept is 4. But what about the x-intercepts? Plus or minus a negative 4. Because we bring the 4 over, it becomes negative 4 inside the square root. And you guys learnt about I. But in methods, you just graph it like that. So how can it be I? It's called the Argand diagram. That's today's lesson. Or the complex plane. Looks like the Cartesian plane. Okay, this is the difference. We have the real axis and the imaginary axis. And Z is the letter we use to represent a complex number. Okay, so like if I had a complex number Z1 equals 1 plus I, you go 1 in the real direction and 1 in the imaginary direction. So I'll use a different color. It always starts from the origin, okay? It always starts from the origin. So that is Z1. So just like vectors, you can do scalar multiplication. So if I did 3, change colors again, 3Z1, what would 3Z1 look like numerically? 3 plus 3i. So I'm just pretty much extending it out. Yeah? So that's 3Z1. The coefficient for the real is 3. The coefficient for the imaginary is 3. So that's scalar multiplication on the Argand diagram or the Argand plane. Okay, what about if I have another complex number? So let's make it 2 plus 4i. In your books, add Z1 plus Z2. Z1 plus Z2. You got the 1. Remember we add the reals together, yeah? 1 plus 2. And we add the imaginaries together. I plus 4i. 3 plus 5i. We've got 3 in the real for Z1 plus Z2. 5 in the imaginary for Z1 plus Z2. So it's going all the way over here. Okay, who remembers what a complex conjugate is? So what do you think is going to happen to Z2 when I graph its conjugate? So when you graph the conjugate, you're like flipping it across the real axis. So the conjugate of Z2 would be down here with a line over the top. Because we've made it 2 plus, instead of 4i, it's minus 4i. So if you want to rotate, I don't know, for some reason you want to rotate your complex number by 90 degrees, you multiply your complex number by I. Z1 times I is I plus I squared, which is I minus 1, which is Badum. So now we have a 90-degree angle. So that's your fifth dot point. If you want to rotate a complex number 90 degrees, multiply it by I. And that's it for today.